Hello everyone, here I am glad to introduce our work, MonoNeRD, NeRF-like representations for monocular 3D object detection. Monocular 3D detection is an active research topic in the computer vision community due to its convenience, low cost and wide range of applications. It takes an RGB image as input and predicts 3D boxes in the 3D space. In this area, it is common practice to utilize scene geometric clues to enhance the detector's performance. However, many existing works adopt these clues explicitly, such as estimating a depth map and backprojecting it into 3D space. This explicit methodology induces sparsity in 3D representations due to the increased dimensionality from 2D to 3D, and leads to substantial information loss, especially for distant and occluded objects. In this paper, we point out that extracting dense 3D representations from monocular images is non-trivial and propose MonoNeRD to solve this problem. Specifically, we propose to model scenes with signed distance functions, SDF, to facilitate the production of dense 3D representations. Then we treat these representations as neural radiance fields and employ volume rendering to recover RGB images and depth maps. Such dense 3D geometry and occupancy information can facilitate the detection process. Extensive evaluations on Kitty and Waymo demonstrate MonoNeRD achieves state-of-the-art results. Here is our overall framework. We follow the paradigm of CADDN and design several components to achieve our goal. The red dashed box represents our position-aware frustum construction process. The yellow dashed box stands for the transformation from SDF to volume density. The green and blue boxes show how to get corresponding visualizations or prediction results from this pipeline. Here is our position-aware frustum construction. This process allows us to generate features with position information and map the image features to 3D space without causing ambiguous spatial relations. Here is the example of the transformation from SDF to density. Instead of predicting per pixel depth, we predict the signed distance for each position. Such SDF-based modeling enables continuous scene representations and easy to interpolate. We adopt the same modeling as Ball SDF, which allows to transform SDF to volume density with a cumulative distribution function of the Laplace distribution. Moreover, we can render from other views as long as the view's frustum overlaps with the original view's frustum. This allows our NeRF-like representations to get extra supervisions. This is the comparison on the Kitty test set. The red refers to the highest result and blue is the second highest result. Our method achieves state-of-the-art results and shows superiority especially on the hard setting. This means MonoNeRD can better handle distant and occluded objects. This is the comparison in the Waymo val set. Our method yields the best performance compared with state-of-the-art methods by a large margin. We also provide some qualitative results. Here is the visualizations of BEV accumulated density maps corresponding to different supervisions. Experiment 1 uses stereo images as depth supervision. Experiment 2 uses LiDAR depth labels as depth supervision. Experiment 3 uses both supervisions. Experiment 4 uses LiDAR depth labels for depth supervision and SDF loss for direct 3D supervision. Experiment 5 uses all supervisions. And this is the corresponding rendered depth maps and RGB images. Finally, we provide a 3D occupancy demo video on the Kitty dataset. That's all. Thank you.